Okay, so good evening and welcome to this PMRF live session of hello. Okay, so let me use the mics. Hello. So, good evening everyone and welcome to this PMRF live session of real-time digital signal processing. This is finally the end week, the last week of this course, and let's hold on a second. Where is this sound coming from? Hello, hello. Okay, okay. Okay, so for disturbance, good evening and welcome to the last session. It's not the last, but the last week of the PMRF NPTEL session on real-time digital signal processing. So we have covered all the topics that have been mentioned in the course, and let's have a brief look at what we have covered till now. So if we go back to the slides of okay, so here are the slides of our the first week. In the first that slides that I've covered in the first week. So let's review what has been covered till now. So basically, the course was intended to be designed. The course was designed to allow all the learners who are on this active platform to become good DSP engineers. Well, a single course cannot actually equip you with all the tools, but this course was a brief summary, a brief overview of what are the minimum requirements to be the same. So we had three modules: signal analysis and filters, frequency domain analysis, and the applications of real-time signal processing. So what did you see in signal analysis and filters? In the first week, we had covered the basics of real-time signal processing. Starting from the number systems, we had a good discussion on the fixed point, floating point systems. Okay, which one is better, when to use what, when not to use the other. Then different DSP architectures such as the Howard architecture and then the von Neumann architecture. generally we talk about the von Neumann architecture only, and then how in the data flow, instruction flow takes place. And that was a brief discussion DSP architecture. You can refer to separate courses on computer architecture. Then in week 2 we talked about we went into the deep aspects of VLSI signal processing. So basically I had mentioned multiple times, you can refer to Professor Keshav K. Parhi's book by the same name, or as well as his video lectures on YouTube. So he had covered 5 filters on the basic, then the concepts of pipelining and parallel processing for high speed as well as low power applications, what is cut set timing, how you can use pipelines to increase the speed of your filter, where to insert a pipeline, where not to insert a pipeline, okay, and how you can modify the structure of your filters in order to have lower power. And then in week 3 and 4 we had a great talk on we had great discussion on IR filters, their stability, and we also had a talk on quantization effects of the filters, okay. Then in the second module, that is spectral analysis tools, in the first had a discussion on discrete Fourier transform. So where and why did discrete Fourier transform come from? So actually we mentioned that all the analysis that we did in our earlier signals and systems course, which is actually the prerequisite for this course, such as the transforms that I was talking about, like continuous time Fourier transform, discrete time Fourier transform, Z transforms as well you can consider. So they were either continuous in either amplitude or the frequency domain, in the time, or they were either continuous in the time domain or the frequency domain, or both, okay. But then we are talking about real-time implementations, and when you implement in real time, you are actually talking about computers, finite memory systems, okay. So when you have finite memory systems, you cannot have something some infinite precision numbers being stored on your system, like let's say pi has infinite digits, 3.1415926 and so on. You can go on and you will never stop. But can we actually store pi on a computer? Answer is no. But can I store up to a certain number of digits or certain number of bits, which we see in our binary number system? Yes. And how many bits can you store? So that depends upon an application, how much error can you tolerate. So based on your system, based on your application, you decide upon the number of bits, and that many bits you use. So that's why we actually let's get back to the transforms. So that's why we cannot deal with transforms which have some sort of a continuity in any either of the domains, either time or frequency. So basically, if you see our systems, digital systems, they actually sample the continuous time signals into discrete time signals, okay. So in the time domain, now you have discrete signals. Moreover, when you convert them into frequency domain, now you cannot do DTFT, because the frequency again ranges from minus infinity to infinity, or when you sample it, it actually ranges from minus pi to pi, okay. So 2 pi periods are all the same. Now when you have these 2 pi periods, that's a real line. Even if it's a finite range, the number of frequencies over here are infinite. So can you store can you store our frequency response of these discrete time filters in a computer? Again, no. So what do? The frequency domain is also sampled, discretized into frequency points, okay. So now you have discrete in time and discrete in frequency. This is a scenario. So that's where the discrete Fourier transform comes into picture. Okay, so we had a lot of mathematics to deal with in week 4, and in week 5 we did a bit more math with DFT, okay. So we had something called the w and minus k in term, which are called the twiddle factors, right? So twiddle factors, their properties, symmetry, periodicity, okay, so these were discussed. And then we saw the computational complexity of our discrete Fourier transform. So we observed that for an n-point DFT, the number of multiplications are of the order of O(n) square. Okay, so you realize that as you increase the value of n, the computational complexity rises by order of square. Now you understand that if when I do a 4-point DFT versus a 256-point DFT, 256 points, 1024 points, these are quite common numbers. So you can't deal with such humongous numbers of DFT operations. So in that case, we use the operation or the algorithm called fast Fourier transform. So it's not another kind of transform, but rather it's a faster implementation of the DFT algorithm. Then we had to talk about the fast Fourier transform structures, decimation in time, decimation in frequency, how do their structures look like, as well as the important fundamental units of FFT are, if you remember, the butterfly structure and the twiddle factors. Okay, so these are the two fundamental components which build up your Fourier transform. And then in week 6 we talked more about fast Fourier transform, in which we talked about real continuous signals. So earlier when we were talking about these transforms, they were simple n-point transforms. So what happened, you have a single chunk of endpoints, you work on the endpoints and that's it. But in real life your signals are not like that. You have a continuous stream of data. For example, I'm speaking with you, this video is coming towards you, so you have a continuous stream of signals. So so let's say the recording started at 8 p.m. and it's now 8:23. So 23 minutes of continuous video is being recorded and sent across this wireless channel. Now this will go on till 10 p.m. I suppose. So how many points of FFT will you use? And it's going on live, you don't have all the points. So let's suppose you start from 0 to 23, and then how will you proceed? So that's where the two subtle concepts of overlap add and overlap save come into picture. What do? They actually so basically, before understanding what overlap add and overlap save do, you need to understand how do you deal with these signals in time domain. So basically, when you have the continuous stream of samples coming in, you break them into various data chunks of, let's say, 10 milliseconds, 20 milliseconds. Okay, these are standard lengths. You store that entire set of 10 milliseconds data into a buffer and then operate upon that buffer. Okay, so you take these batches of data and operate upon them. Now you understand that these batches are discrete, but then when you want to take the overall FFT, they have these two batches have some kind of connection with one another. You're taking each of these batches individual transforms, but then when you want to see the overall transform, then there must be some combination between them. So in order to account for that, we use the overlap add and overlap save mechanisms. And finally, we have the final third module, which is the real-time signal processing applications. So in week 7 we had discussion on what is signal correlation. So basically we started with some statistical definition of we had some discussion on probability distribution, some important characteristics like mean, variance, covariance, correlation coefficient, and then when we talk about correlation or correlation coefficient, from there we went on to signal correlation. So earlier we were talking about random variables and then we went on to signals. And once you had this probability and statistical background clear, we moved on to adaptive filters. So the earlier filters which we had been discussing in which section? In the first module, we were talking about FR and IR filters. So in those cases, the filters had constant coefficients. But now what is happening? In real life scenarios, you may want to detect some kind of signal, you may want to estimate some kind of a channel, for example channel equalizers or noise cancellation. Okay, so the to and fro medium, the receiver and transmitter medium, has to be estimated first. Okay, and you do not have a good idea of how the system behaves, so that's where adaptive filters come into picture. And in fact, these adaptive filters are nothing but the basis of machine learning and deep learning algorithms. In fact, when we talk about adaptive filters, when we talked about adaptive filters in detail, we talked about cost function, the error curve, gradient descent. Okay, so, and then these concepts, if you study in machine learning and deep learning, you encounter the same thing. The only difference is that in that case, in the adaptive filter case, we are dealing with real life signals like voice, and in those other cases you will be dealing with static samples like images or maybe videos, and then trying to get some kind of a rule. Okay, so for example, the rule in our case, okay, the hypothesis that you call in machine learning is the filter coefficients. Okay, the filter coefficients that we want to learn. How do we learn? We have some desired signal, we have an input signal, and then based on the error, based on how we estimate there is an error, and then we try to reduce that error and get the desired coefficients. And if you have studied some machine learning or deep learning courses, you must have learned about something called the stochastic gradient descent, where you use single sample and use that cost function of corresponding to single sample, not the entire set. Okay, and that's what actually you use in the least mean square or the LMS algorithm. When we talked about the adaptive filters, we had a early good notion of an ideal filter, the Wiener filter, the optimal filter. How was that obtained? That we saw W opt is R inverse of P. What was R? R was the autocorrelation coefficient, autocorrelation matrix of the input signal, and P was the correlation vector between the desired signal and the input signal. Okay, and W opt is R inverse of P. Now first of all, there are two things. In computation of an inverse is really tough, and especially in hardware that's even more difficult. That's the first point. Moreover, the signal statistics may change with time. Okay, so you have some R inverse earlier, based on that you have calculated your W optimal. Now if your signal statistics changes, then the R inverse phi will change, and you have fixed a W opt beforehand, so now you can't change it anymore. So you always require something else, some adaptivity in your filter. That's where the least mean square algorithm comes into picture, and you try to simplify the implementation. You remove all the R inverse and all the expectation terms and reduce them to a single sample. Okay, and we talked about LMS algorithm, and then the error curves. How does the error drop as a function of as time evolves? And then based on the different learning rates, there is something called learning parameter, which determines how fast or slow your error is decaying, how fast or slow will you reach the steady state. We have different mean square errors levels, noise levels. Okay, so for example, if your update parameter or mu is very small, then you will require a lot of iterations to reach the ideal optimal weight vector, but then you will reach the lowest possible or the actual noise floor. But in case you take mu some high value, not very high, but you take it, consider it to be high enough, then what you will observe is that you're settling down to some mean square error which is above the noise floor. Okay, why did it happen? Because you're not giving enough iterations, or you're not jumping too fast around the W optimal point. You're not converging down to the W optimal. And if it's too fast, then you may diverge up the error gradient surface. The bowl shape or the parabola that I shown over to you in 3D, it's called the bowl. Okay, there's a bowl shape. It's called the error gradient surface. And then in week 9 we had discussed about eco and graphic equalizers. So that was quite theoretical topic in nature. We talked about how we can manipulate the frequency response of each portion of the audio spectrum to gain some kind of a desired audio effect, maybe let's say pop, rock, jazz, or whatever you want. So computers also come with those predefined equalizer filters where these treble, bass, and mid, these frequencies can be adjusted using sliders. So there were various standards, industry audio telecommunication standards that were mentioned. And then in week 10 we were talking about speech coding. Okay, so what was speech coding all about? So basically speech is a very special signal because the samples are very nicely correlated with each other. So given one sample, and if you have some idea of the signal statistics, you can very well predict the next sample. And due to the good correlation, the prediction and the actual sample that comes, the difference between them is quite small. And rather than sending the entire sample, you can send the difference between the two. So you end up lowering the transmission rate. Okay, so it all boiled down to sending things at lower transmission rate. And then we had a lot of discussion regarding the how the speech is modeled. Okay, all these parametric, the vocoders, parametric encoders, okay, mixed encoders, yeah, and code book transforms. Then in week 11, that was the previous week, we jumped into image processing. Okay, so you can see how we have moved from simple number, a unit sample, okay, a sample represented by a single number, how we represent that number using bits, okay, individual bits. Then all the bit samples together make up a signal, how we process that signal using simple filters, and then you change the coefficient in the filters, and then you use a bunch of these filters in equalizers as well as coding techniques as well. You have a huge bank of filters. And then we move to this image processing domain. You see how the course has evolved, and you have learned a good spectrum of things. Although it's not the complete spectrum, okay, there are a lot more things in real time signal processing. But then in discrete cosine transform module we talked about images. Okay, so 2D images, 2D signals, x-axis and y-axis, you have a matrix of data. Again, you exploit redundancy in one form or the other, just like speech coding has its redundancy in the form of correlation between its samples. In the images also, in reality, the any two adjacent pixels or in a neighborhood of pixels do not change their values drastically. I mean, that happens with real signals. For example, if you can see the entire screen, you will see that if you take out small chunks of the screen, then you won't see much variation in the pixels. If you had to zoom into this picture, okay, just because everything is perfect and fine over here does not mean that the image is continuous. It's actually pixelated. Okay, if you zoom in, you will get pixelated images, and you will see that the pixel values are very close to each other. And since they are close to each other, why are you sending the entire values? These are 8-bit numbers in general, 0 to 255. I had even taken out the app and showed you all the values of RGB. So instead of sending all the 8 values, 8 into 3, especially for color images, why didn't you send a difference? So we talked about sending the difference between the pixel values, the p values that were shown, different encoding schemes in a JPEG, as well as the encoding schemes for the DC and AC components. We talked about the discrete cosine transform. It's a real transform that you perform on the images. You compress, you transform your signal from the spatial domain. Earlier signals that you're talking about audio were in time domain, Here you talk about the space domain. Okay, x and y axis, it's in space. So a spatial domain image is converted into a frequency domain, a signal, and that's also 2D. But then you take 8 blocks of 8. Okay, blocks of 8 in general you took based on JPEG. You take blocks of 8 and then do all kinds of processing. For example, you encode the image and then you do a prediction of the image and then send the difference between the predicted and the actual pixel value. On the DCT components, an important point was that the human vision is very less sensitive to high frequency coefficients and more sensitive to low frequency components. And in reality, that in DC you take a DCT transform, then the high frequency coefficients can be easily truncated, and you can send the low frequency components which are very small in number. Okay, and then you can achieve great bandwidth for transmission. Okay, so, and this is a week 12 where we had talked about lab sessions, but then lab sessions are not possible in this PMRF online session. So maybe I can revise all that has been mentioned in today's class. Okay, so let's look back at the question. So in a DSP processor, if A and B, these are two digital words, A is M bits and N bits must be multiplied. The maximum number of bits required to represent their product is maximum of how much? M plus N bits, M or N bits, M minus N bits, or max of M or N bits. Let's see what we had learned in lectures, and I'll take a practical example and show you. So bit expansion, so what does it mention? So it assumes that let the number of bits be R bits. So an R bit number will range from 0 to the power minus 1. Okay, so rather than doing it this way, let me go back. Okay, so let's review with the number system. So what were we talking about? We are talking about number system, basically the unsigned numbers. Where do you find unsigned numbers? Now that we have completed the course, then we will try to move to and fro from across the different modules. Okay, so unsigned numbers are found in images, the for pixels. So an R bit unsigned number occupies the range 0 to 2 to the power R minus 1. Okay, so for example, when I talk about an 8-bit unsigned number, what does it, how much, what range does it occupy? So it occupies 0 to this 2 to the power 8 minus 1, 2 to the power 8 is 64, it's 256 minus 1, that is 255. Okay, so that is the range that your pixel calculates. Okay, and when you have unsigned numbers, in fact, if you look for papers on multipliers, okay, you will see a lot of papers which deal with 8 cross 8 multipliers, where your input A as well as B are both of them are 8-bit and they are unsigned. Okay, so the lowest number that you can represent is all zeros, and that's obviously 0, and the highest number that you can represent is all ones. Okay, so this was a side note. If you look into papers, so most of them actually, most of the papers that you see will deal with 8 cross 8 8 cross 8 multipliers, because they are quite popular in image processing or other signal processing. These numbers are very favorite and in fact used in many systems. Okay, so these are your unsigned numbers and they are very simple to deal with. But you observe one thing, you can't add, if you add two unsigned numbers, okay, the lowest possible that you can get is how much? So for them to do the output to be the lowest, both the adder and end, okay, both A and B have to be the lowest. That's 0 plus 0 equals 0. And what has to be the highest? So both of them, 255 plus 255, how much does that turn out to be? 5 plus 5 is 10, 5 plus 5 10 11, 510. So it's less than 512, which is close to 2 to the power 9. But then you realize that you cannot represent 510 by 8 bits, you require 9 bits. Okay, so when you add two n-bit unsigned numbers, you will get an n plus 1 bit unsigned number. Okay, that's for sure. Now we deal some with the signed numbers, and we frequently come across them. For example, the voice that you are hearing will actually be represented using signed numbers, and we will be talking about 2's complement representation. And actually 2's complement representation is chosen because it is hardware friendly. So if you look at other forms of representation, their corresponding additions or multiplications will require extra logic circuits for decoding whether it is positive. Okay, so if you do addition of two signed numbers using two's without two's complement, some other representation such as the signed representation or one's complement, then the adder or adder will require extra logic circuit for decoding which is positive, which is negative, which is greater, which is lesser. But then 2's complement does not require any of these things. If both the numbers and 2's complement, you can use the same hardware for addition of positive, negative and mixed numbers. So for signed numbers, for r bit number occupies the range -2 to the power r minus 1 to 2 to the power r minus 1 minus 1. Okay, so for the 8-bit case, how much will it occupy? So it's 2 to the power 7, that's -128 to 127. Fine, And in this case as well, two n-bit signed numbers when added, they give n plus 1 bit signed number. And in case you want to fix it to in bit, then if the value, if the sum actually lies beyond this range, then you will have something called overflow. Okay, and when does overflow occur? So let's say this number a n minus 1, a n minus 2, so on till a0, b is b n minus 1, b n minus 2, so on till b0, and the sum says sn minus 1, sn minus 2, s0. Okay, so in order to detect overflow, we look at these 3 bits. So if an minus 1, bn minus 1, both of them are 1. Now, okay, so I should have actually shown this. So if the MSB of a 2's complement number is 1, that means the number is negative. And if the LSB, and if the corresponding MSB is 0, then the number is positive. And how do the numbers look like? On the negative scale, minus 128 will look like 1, and all the other digits are 0. All the other bits are 0. As you keep moving towards lesser negative numbers and reach minus 1, you will obtain all ones. So if you notice the numbers in case of 2's sign representation, 2's complement representation, the negative numbers with MSB equal to 1, negative numbers have MSB equal to 1, the higher the number of total number of ones present in the number, the lesser negative is the number. The more you see zeros in it and the MSB is 1, understand that the number is highly negative. And in case of positive numbers, it's the opposite case. So in 0, it's all zeros, and in 127, only the MSB is 0 and rest all are ones. Max zeros except MSB, max ones except MSB. So same holds for 2 of them. Okay, so now if an minus 1 and bn minus 1 are suppose 1, okay, and sn minus 1 turns out to be 0, and when I do a 0 in the digital circuits, you must have learned when you represent the 0 bit for the canonical expression of the min terms, you put a bar over that. Okay, I'm doing sum of product terms. Okay, SOP representation. So the literal that that gives corresponds to an output of 1 when it is 0 itself has a bar over it. Okay, if this is a scenario that an minus 1 is 1, bn minus 1 is 1, and sn minus 1 is 0, or an minus 1 and bn minus 1, both of them are 0, and sn minus 1 is 1, what do they represent? You see, the MSB of A and B are 1, which means A and B are negative numbers, and when you add two negative numbers, what are you supposed to get? A negative number. But then Sn minus 1 is 0, that means the MSB is 0, and hence it is a positive number. Is that supposed to happen? Not at all. But why is it happening? Because the final output does not have enough space to store an n plus 1 bit number, and that's why you're getting such a weird behavior, and this is called an overflow. I'll show you an example. Similarly, the opposite case, when an minus 1 and bn minus 1, the MSBs are 0, which is a positive number, and you are supposed to get a positive number, which means the MSB is supposed to be 0, but you end up getting a 1, that means your output has overflown the length of the register. Okay, so these are the two conditions for overflow, detecting an overflow. You can also there's also a separate condition on the, I mean it's a similar condition on the carries. Okay, but I'm not showing it over here. So for example, let me give an example of overflow, and we are dealing with integers for now, but overflow in the perspective of okay, let's deal with a integer number only. Let's talk about 4-bit numbers. Okay, what are the 4-bit numbers ranged in form? So that's -8 to 7, right? Okay, so let's consider number 7. And what's 7 in binary? 1 plus 2 plus 4 plus 0, that's 7. And then consider number 3. What's that? 1 plus 2 plus 1 plus 2 is 3. Okay, now let's add them directly. 1 plus 1 gives me a 0 as sum and a 1 as carry, and then it goes into a full adder where 1 is the carry in, 1 is the A and 1 is the B, so it's 1 plus 1 plus 1, sum as 1, carry out as 1. Again 1 and 1 gives me sum 0 and a carry of 1. Here if you look at this, you get a 1. So what do you observe? What is the result? This corresponds to -8, this corresponds to 4, this corresponds to 2, this corresponds to 1. So what do I get? -8 plus 2, that is -6. What am I supposed to get? 7 plus 3, that is 10. Okay, but what I'm getting over here is 10 minus 2 to the power 4. That's 10 minus 16 equals -6. So what has happened over here? It's an overflow. And how do we solve this overflow? We solve this overflow by something called the sign bit extension. Let me show you the example. So what is sign bit extension? Since the output is supposed to be a 5-bit number, we extend the inputs themselves to 5-bit. Okay, we know that the number is 4-bit, but we extend the sign bit to the left side so that we get 5-bit numbers. So 0 1 1 1, and I give a 0 over here. Similarly 1 1 0 0, and I give extend, see it was a 0 over here. Here also I give a 0. Now I focus on 5 bits. 1 plus 1 gives me 10, 1 plus 1 plus 1 gives me 1 and 1, 1 plus 1 gives me 10. I focus on the 5 bits, and what do I see? This is 1, this is 2, this is 4, this is 8, and this is -16. So what do I get? 8 plus 2, and that's 10. So you get the correct answer by this phenomenon of sign bit extension. So whenever you have a 2's complement summation to be done, and if you want correct answer, okay, you want a correct answer, then always perform sign bit extension in order to avoid any discrepancy. But in case in exam you are asked some question where you are supposed to get the answer in 4 bit itself, then don't do sign bit extension. Okay, perform the arithmetic as shown over here. Okay, this is because they want to check the overflow concept, whether you have checked the overflow or you have directly added the answers. If you directly add the answers and then stick that, it will be incorrect because you have not checked the overflow or you have not done it in the digital format. So what I have done was with integers, and now I will be talking about the fixed point representation. So in the fixed point number representation, we have something called the q m comma n, where m bits are allocated for the integer plus sign and n bits are allocated for the fraction. Okay, so how do I denote this? Q m minus 1, Q m minus 2, Q m minus 3, Q2, Q1, Q0 is the decimal point, and then here enters the fractional portion Qn. This is my sign bit, this is my integer. Actually this entire thing is my integer part, and this is my fractional part. And what are the range of values covered by this number? The range is, so since it's m bits of integer, so m minus 1, okay, remember, because the sign bit is eating up 1 bit, minus 2 to the power m minus 1 to 2 to the power m minus 1 okay, so 2 to the power m minus 1 is excluded, and you have a resolution of 2 to the power minus n, and this corresponds to the, okay, there should be negative sign over here, the last bit over here, that corresponds to 2 to the power n. And how do you calculate the value of any number? So that is summation over qi 2 to the power I summation from minus n to m minus 2 minus q of m minus 1, because it is a sign bit, we give a negative sign, 2 to the power m minus 1. This is how you evaluate the entire value. So now in exam you can be given a 4-bit value and general q1.3 generally, and you are given this number 1011. Okay, how do you find the value? They won't give any decimal sign, So it's q 1.3. So you need to understand there will be one integer plus sign bit case. So this will be your decimal, because one bit over here and the rest 3 bits over here. So this place corresponds to 2 to the power 0 before the to the left of the decimal place. This one corresponds to 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. When you calculate the value, it should be negative because this is the MSB. Minus 2 to the power 0 plus 2 to the power minus 2 minus 3. And the sum is minus 1 plus 0.25 plus 0.125. That's 0.375. That turns out to be 5 plus 5 10, 7 plus 1 8, 9, 3 4.625. Okay. Similarly, when you get other problems, you will be able to solve them. For example, if I get back to the slides. Okay, so I talked about this. Okay, so here they mentioned Q15 format. So in case you are giving something like Q5, Q3, Q5, Q15, then what do you need to assume? You need to assume there's only one sign bit, unless you observe something special in the options. Q1.5, which is 6 bits, Q15, Q1.15, which is 16 bits. Okay, this will be a representation. So some important topics of number system I have mentioned, which may come in your exam, because that's been, I've seen this a lot in the practice questions. And then we obviously have these theoretical concepts of scaling, why we need scaling. Okay, so you can refer to my first lecture video. Then shifting. Okay, so you also need to check out the different addressing modes of the DSP processors, like direct, indirect, circular, bit reversed. When do you use bit reversed, and when do you use circular used in FR filters, as you remember, it's 0 h1 h2 back to h7 and then again 0. Okay, because it is going in a cyclic manner. And bit reversed, if you remember the FFT lecture, we talked about so bit reversed addressing mode. What happens in the bit reversed addressing mode? So you had the input signals x0, x1, x2, x3, x4, x5, x6, xm. This is the 8-point FFT. Zero is represented by 00, 1 is represented by 001, 2 is represented by 010, and so on. I am writing all of them over here. 101, 10, and 111. So how does the outputs in this, and this is the decimation in time. No, this is not the decimation time, this is the decimation in frequency. Okay. So if you take these 000 bits and you take the mirror image, you get 000 back. Similarly for 10001 you get 100, 2 remains the same, 011 becomes 110. Same for the rest of the images, 111 and 111. And now you check the corresponding outputs, you get x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. This is the bit reversed addressing modes. And what was the circular mode used for? H0, let's say H0, H1, H2, H3. So time index n, we have 0 and then 1 and then 2 and then 3, and again when you are at cycle 4, so n equal to 4, so you actually take n modulo 4, so 4, 5, 6, 7, all of them will be jumping back to these numbers. Okay, so H0, H1, H2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so everything moves or rotates in this direction. This is the circular addressing mode. Okay, so and then we talked about parallelism, how it improves. Okay, 2's complement. And then in week 2, okay, so this was the suggested book, the VLSI Digital Signal Processing Systems. We talked about FIR filter design. FIR filters can actually never be derived from the analog filters, because analog filters are inherently IIR systems. You give an input to them, but then their output will never stop. They will keep on decaying, but like an exponential sinusoid or something, exponential curve, like an RC filters impulse response. And if you have studied analog circuits or network theory, then having looked at the transfer functions and the phase response of the analog circuits, you will have never found the phase response to be linear. You will find them in terms of tan inverse of omega t, tan inverse of s minus 1 by s plus 1, something of that sort. But FIR filters are often designed to have linear phase, okay, but that's not possible in the analog filters. Okay, so all of these were covered in the previous weeks, in the previous lectures. Please refer to them. Linear phase filters, you see this kind of symmetry that you need to look at. The last coefficient is equal to the first coefficient and so on. Okay, and then the concept of group delay. Okay, so a bit on pipelining can be explained now. So let me explain. Feed forward pipelining. So basically, let's consider an 3-tap FIR filter. Okay, so you have the input signal xn, then you have the first delay xn minus 1 and the second delay giving you x of n minus 2. You take in the first step multiplied by h naught, second tab multiplied by h1, third tab multiplied by h2. And then we define the concept of critical path, which is the longest path in the circuit. And what were the 4 types of critical path? If you remember, they were from input to output, and note that the critical paths do not have any delay element or registers between them. So we have input to output, input to register, register to output, and register to register. Okay, so in this scenario you have actually 2 critical paths with the same delay. And what is the critical path delay? So the time taken for a multiplier to complete its multiplication is, let's say, Tm, and the same for an adder is Ta. Okay, the CPD, if I look at, so first you need to go to the multiplier completely, so it's Tm, and then the first adder, and then the second adder, so 2Ta. And so, and this is the something called it direct form or DF filter. So for an n-tap filter, the CPD is Tm plus n minus 1 Ta. So as n increases, your critical path decreases. And what does that mean? This means that the clock period, because you are running these registers, they are all driven by clock. Your sample rate or the clock period has to be greater than equal to TCPD, so that the circuit gives correct results properly, so that there is reliability. T clock has to be greater than equal to Tm plus n minus 1 into Ta. And so what does it mean? Maximum clock frequency is 1 upon Tm plus n minus 1 Ta. So that means that the higher your filter order, the lower will be your speed of operation. So this is a really concerning scenario when you want to build fast circuits. So in that case, what do? We do something called feed forward pipelining. There are 2 ways to solve this problem. One is the feed forward pipelining, and the second one is the transposition theorem. So in feed forward pipelining, let's suppose you have some kind of a path like this. Okay, so in these cases, these dots over here are being replaced, are actually representing the adders and multipliers. Okay, so feed forward path says that whenever you have certain number of edges or lines going in the same direction. Note that all of them are moving in single direction and same direction. Okay, now you first try to cut this line and check if after cutting the line the graph becomes disjointed, means the graph gets divided into two disjoint graphs or not. That means that, let's suppose if I cut only these two lines, then it does not become disjoint, because you still have this link, downward links, okay, that is connecting the X with the rest of the world. But if you actually cut the entire thing over here, then you actually get something like this and the rest of the world connected. Okay, so such feed forward cut sets, these are called feed forward cut sets. Okay, so such kind of feed forward cut sets are actually allowed, and when you have such cut sets you can place delay elements onto them. Okay, so rather than drawing the delay elements, I write D over them. There was no delay elements, we had a D. No element, we had a D. There's already D, so 2D. Okay, so this is called, simply this is the concept of feed forward pipelining. So now if we look at the filter, so there are multiple feed forward cut sets that I can show you. For example, this is one cut set, all of them moving in the forward direction. This is one cut set cutting this and this. This is another valid cut set. Okay, so if I consider the pink one, and I get a D over here, I get a D over here, and I get a D over here. So as I get a D over here, I have TM and TM and TM. So that's restricting my path, these delays are restricting my path. And then another path I can see over here, one is this, another one is this. Okay, so it will be either the multiplier delay or the two added delay. Okay, so the first possible delay is maximum of Tm comma 2Ta, or if we had n of them, we could have done maximum of Tm and n minus 1 Ta. So you observe over here that earlier we had Tm plus n minus 1 Ta, right? Now we are having maximum of Tm comma n minus 1 Ta. So isn't that decreasing your clock minimum clock rate, minimum clock duration, or the increasing the clock frequency? So that's one advantage of pipelining, you're increasing the clock frequency. Now let's suppose we look at these purple color card sets. So I place a D over here, and when I mean these colors, I ignore the pink ones, and I insert a D over here. So here also a D needs to be inserted, so this will indirectly refer to 2D. Similarly 2D. So in this case, what are our critical paths look like? So this and this. Okay, so even if any of them, so all of them will be in parallel, and these addresses are then being separated by a delay, so we cannot consider them. So in the second case, the critical path is Tm plus Ta. You see, irrespective of, so now in the second case is even better, because you increase, you have decreased the clock period to a even lower value, and this is independent of the filter order. Okay, that further improves your clock frequency. But now there's a this does not happen for free. Okay, these delay elements themselves incur some power. Okay, these delay elements, they eat up area, obviously, because they are made of these NAND gates in feedback. If you have studied in digital electronics, they eat up area, they increase power consumption to a good extent because they are being toggled by a clock. Okay, and we are considering ideal registers over here. In reality, if you study static timing analysis, then these delays or these registers have something called the setup time and hold time. Okay, one, why are they important? Because you cannot arbitrarily give a clock signal and expect data to be latched into the register at any point of time. You need to have certain difference in timing intervals, certain differences, so that the data is latched in properly and safely. Okay. And when you have T setup and T hold, okay, when you have T setup and you have T hold, you actually impose more of a constraint on your timing periods. We have just taken TM and TA, but in reality T setup and T hold will also play an important role, and especially in real life integrated circuits. There are clock skews, these clocks are sent by metal wires, so based on the metal wire length you have corresponding delays associated. So there's an entire area of work that goes into how you distribute your clock, how you play with the clock free signals. Okay, so that's, we won't delve deep into this further, but then in fact, when you have two of these delay elements placed to each other, close to each other, and in case you want to synthesize these circuits, then these two delays just being close to each other, how much close they are, and then the T hold plays an important role in this. Okay, so you may have timing violations. So if you study static time analysis, if you're someone who is interested in VLSI, then you can go forward, read about this. There are a lot of material in the YouTube now. Okay, I'm not discussing about this further. So that was the feed forward pipelining, and now I'll talk about last concept for today. So because I'm focusing a bit on solving problems, okay, that is the, let me know this, transposition theorem. So what does it say? It says that you exchange your input and output, reverse all arrows, multipliers and delays stay as it is, and this is something called the splitter node. I mean, when a node bifurcates into two. So for example, something like this. Okay, so one node breaks up into two. Okay, splitter node and adder node. So two signals combine to become one. This is splitter, this is adder. They are interchanged. Okay, so this is what the transposition theorem asks us to do. Okay, actually there is a big mathematical matrix based framework, but due to lack of time and as it is outside the scope of our course, I'm not covering it. Okay, but remember, you can in fact check out Professor Parhi's lectures and his book as well. He talks about the transposition as a general matrix manipulation. Okay, so if we look at our filter xn d a1 yn. Okay, now what should we do? First interchange input and output. Let me do color coding so that all the steps are okay. So we have interchanged them. Now we reverse the arrow directions except the multiplier constant coefficient multipliers. Okay, they will remain unchanged. So and finally what do we do? Replace the, so these were the adders over here, so now you replace them like splitters, and the splitters over here. Okay, let me do color coding. So and I should, okay, this is 0. This is same as not having any adder, and I should also mark the delay elements and the multipliers also. D. Okay, so this is finally our filter, and if I actually try to show you how it looks, okay. Now see, in this case, when you've done transposition, what is the critical path? TM plus TA. So transposition also gave us the same answer. Okay, but then you see over here the number of delays are unchanged, but over here for the same delay we had introduced 1, 2, 3, 4 extra delays. Okay, so you see, transposition a smarter method. Okay, so I think I can stop this class today. So on Friday we'll have a 1 hour final session. Okay, so please attend them. Thank you very much. Good night.